Hello everyone, welcome to this session. So in this session, we will talk about objectives. So in the last session, we have said that in the problem, you can have more than one constraint. And you can also have more than one objective. This is what we will focus on in this session. So here I provide a bi-objective continuous optimization problem. So bi-objective means two objectives. So you can have 3 objectives, 4 objectives, that's no problem. So let's see the problem. So the first objective, maximum f1 from x1 to xn, this is the decision variables. And also we have max f2 x1 to xn. So the x belongs to the decision space D, and D belongs to the real domain. So we can see it's here. And minimization is similar. As we have said before, we just add a negative sign to f, the maximization problem become a minimization problem. However, the real problem is a trade-off of the f1 and f2. So often the f1 and f2, they conflict with each other. So you often can't get a solution that is both good at f1 and f2 together. So normally you get some solution where f1 is good, but f2 is bad. And vice versa. Maybe you get someone f2 is good, but f1 is bad. Right? So the problem is that in this case, how should we measure the solution quality? So clearly this is very different from the single objective. Single objective for maximization, bigger is better. But there are 2 of them. And the two objectives are conflict with each other. So how to measure the solution quality in this case, right? So such problems is widely seen in the real-world engineering application. So here I give you one example. So now you are designing a controllable switch. So this one, as you can see here, this is an isolated gate bipolar transistor. We call it IGBT, semiconductor controllable switch. We have 2 objectives. First of all, we want the failure rate to be as low as possible. Lower failure rate, the better. Meanwhile, we want the cost to be as low as possible as well. But however, normally when we make the failure rate become low, the cost raise becomes higher. So these 2 conflict with each other. Then, how to decide which solution is better? Before that, we need to introduce a concept which we call domination. Domination is to solve the problems of which solutions are optimal. Here we can see 4 solutions, x1, x2, x3, x4. Those 4 solutions. In terms of f1x and f2x, each of them will have a f1x value and a f2x value. So we can see here the x1 and x2, the f2 value is the same, but f1 value, x1 is better than x2. And for the x2, x3, and x4, we can see in terms of the x2 value, go this way, it becomes better. But for f1 value, if we go through this way, it becomes worse. So let's see how to rank these 4 solutions by the domination concept. So for any 2 candidate solutions, x and y, we only have several conditions, right? So if x dominates y, this means what? X is not worse than y in any objectives. So here we consider maximization. So fx is larger than or equal to fy, right? Larger than or equal to, this means not worse. And in at least one objective, x is strictly better than y. This means there is no equal to fx larger than fy, right? So we can see this is a domination. So if x dominates y, considering maximization, is like that. So in this way, for any 2 solutions, x and y, we only have 3 conditions. X dominates y, y dominates x, or x and y can't be compared with each other. So as we can see for these 4 solutions, x1 dominate x2, because in terms of x2, fx1 is larger than or equal to, here is equal to fx2 in terms of f2. But in f1, x1 is strictly better than x2, right? x2, x3, x4, these three solutions, we can't compare them each other, because for one objective is better, the other it becomes worse, right? So x1 is better than x2, but does x1 dominate x3 or not? Yes or no? No, right? No, x1 dominates x2, but doesn't dominate x3, because consider f2, the x3's f2 is better than the one for x1, right? So this is a domination concept. Considering the domination, we can collect a set of points without domination. So we can see these blue points we can see here. These blue points, each of them can't be compared with each other. They don't dominate with each other. And we can see the red points, they are dominated by the blue points. So for example, for these blue points x, these are the dominated area. So all the points appeared here are dominated by this x, right? So we have named that these blue points, we call them Pareto front, invented by Pareto, right? A set of non-dominated solutions, we call it Pareto front. Remember, this is maximization, minimization, that is opposite, right? So in these ones, we can see the Pareto optimal solution. So this means they don't dominated by any other solution. For these ones, we call them Pareto optimal solution. So these are the ones that we want to find in multi-objective optimization if we consider a Pareto way, right? Then, based on the Pareto optimal solution, we can have two concepts. The first one, we call it a Pareto set. So these are the set of all the Pareto optimal solutions in the decision space. This means they are x values. And they have the y value. This is one, we call them Pareto optimal front. So this is set, this is front. This front means the objective function values of all the Pareto optimal solutions. So the Pareto front equals to the objective function with the Pareto set, right? So Pareto front is in the objective space. So we can see here in the decision space, this is Pareto set. We calculate their objective function values, and it comes to the objective space, f1, f2. This one, we call it Pareto front. So this is what we want to get for multi-objective optimization. So in multi-objective optimization, we have more than one objectives, and it can also have more than one constraint. So these two can happen at the same time. So the question is that for constrained multi-objective optimization or multi-objective constraint optimization, anyway, how to rank the solutions? This is the question, how to rank the solutions? So we first go to constraint, right? So we can have, if randomly pick two solutions, one of them is feasible, the other is not feasible. Then which one is better? The feasible one. Then if we find two feasible solutions, then we use what? We use a multi-objective way to identify. If we find two infeasible solutions, what we shall do? We compare the constraint violations. Right. So this is the way. Okay, that's all for this session. Thank you very much. Bye-bye.